So, continuing this section, we now want to talk about the complex conjugate theorem. So remember, all these theorems are building up to helping us factor polynomials more and more. So the next theorem says if f of x is a polynomial with real coefficients, which has a complex zero a plus bi, then it also has the zero a minus bi. So if you're given a polynomial that doesn't have anything like plus ix squared, meaning every single number in front of your x is a real number, then if one of your answers is x equals 2 plus 3i, then x equals 2 minus 3i also has to be one of the zeros. The reason is when you multiply your zeros out, remember these zeros represent factors. When you multiply all those factors out, if you don't have all the conjugates together, you'll end up with imaginary coefficients. So whenever you see a complex zero, automatically know that the conjugate is also a zero. So with that, we're going to work backwards. We want to find a fourth degree polynomial f of x with real coefficients, and the zeros x equals 2, 3, and negative I, such that f of 1 is equal to 4. So let's start this off. Since we know x equals 2, 3, and negative I, then that means x is also equal to positive I, because it's the conjugate of negative I. So from there, now that we have all four of our zeros, since it's a degree 4 polynomial, it has to have 4 zeros, we can now change these to their factors. Remember, if x equals 2, then the polynomial has to have the factor x minus 2. Another way to go about that is since x equals 2, if we subtract 2 from each side, then x minus 2 equals 0. That means it's a factor. So we have x minus 2, x minus 3, x plus I, and x minus I. So if we multiply all of these together, we get f of x equals x minus 2, x minus 3i, x plus I, and x minus I. And there's going to be some constant multiplied to this. We'll go ahead and fit an a in here to account for the fact that we don't know if all these factors are multiplied by a 5, for instance. So, multiplying this out, we have f of x equals a times x minus 2 times x minus 3. When we multiply these out, we'll get x squared minus 3x minus 2x plus 6. And when we multiply out the x plus I times x minus I, we'll get x squared minus ix plus ix minus I squared. Simplifying from here, we have f of x equals a times x squared minus 5x plus 6 times x squared. The minus ix and plus ix will cancel out, and minus I squared is the same thing as minus negative 1, so we get plus 1. And now we'll keep multiplying from here. We're almost finished at this point. We have f of x equals a times, we need to distribute the x squared and distribute the positive 1, which gives us x to the 4th minus 5x cubed plus 6x squared. And now when we distribute 1, we're just going to get all three of these terms again. So plus x squared minus 5x and plus 6. So simplifying that, we have f of x equals a times x to the fourth minus 5x cubed plus 7x squared minus 5x plus 6. And now the last thing that we want to do here is solve for this a, and we'll have our function. And we solve for the a by saying f of 1 equals 4. When we plug in 1 into this function, we'll get 4. So 4 is equal to a times 1 to the fourth minus 5 times 1 to the third plus 7 times 1 squared minus 5 times 1 plus 6. So that gives us 4 equals a times 1 to the fourth is just 1 minus 5 times 1 to the third is just minus 5 plus 7 times 1 squared is just plus 7 minus 5 times 1 is minus 5 and then plus 6. We're going to get 4 equals a times 1 minus 5 is negative 4 plus 7 is positive 3 minus 5 is negative 2 plus 6 is positive 4. So 4 equals a times 4. We'll quickly divide each side by 4 to get a equals 1. So that constant that we introduced in the beginning was just a 1. It could have been a 5 or a 20 or a negative 8. It didn't matter, but it ended up just being 1. So we can now say what the final function is. The fourth degree polynomial with these given zeros and with f of 1 equals 4 is 1 times this x to the fourth minus 5x cubed plus 7x squared minus 5x plus 6, meaning it's just x to the fourth minus 5x cubed plus 7x squared minus 5x plus 6. Okay, and now from here we just have one last type of problem to go through. We call this our definition for Descartes' rule of signs, and this is the last thing that we introduce to limit the number of things we have to check when we're trying to factor these polynomials or find their rational zeros, or zeros in general, that is. We say given a polynomial f of x with real coefficients, again, no imaginary coefficients, then the number of positive, that's misspelled, I apologize, the number of positive real zeros is equal to the number of sign changes of the function f of x, or is a multiple of 2 less than that. And the number of negative real zeros is the same thing, but with f of negative x. So this is a very powerful rule. We can quickly check how many positive real zeros we have and how many negative real zeros we have, which again limits the number of things that we have to go through checking. So let's determine the possible number of positive and negative real zeros. Given f of x equals negative x to the fourth minus 3x cubed plus 6x squared minus 4x minus 12. Okay, so going from negative x to the fourth to negative 3x to the third, we do not have a sign change. But now going from negative 3x cubed plus 6x squared we have a sign change. From 6x squared to negative 4x, we have another sign change. But from negative 4x to negative 12, we do not. So that tells us that the positive real zeros, so let me make a note here, the positive real zeros total up to either 2 or an even multiple less than that. So 2 or 4 or 6 or 8 less and so on. In this case, there's only one even multiple less than this, which is 0. You can't have -1 or -8 or -4 positive real zeros. So there are either 2 or 0 positive real zeros. Now we need to do the same thing but with f of negative x. So we'll quickly find f of negative x, and I apologize if this gets a little bit cramped in here. I didn't calculate the room I would need well enough here. So we're finding negative x to the 4th minus 3 times negative x to the 3rd plus 6 times negative x squared minus 4 times negative x minus 12. Simplifying this, we get f of negative x is equal to negative times negative x to the 4th. There are 5 negatives total here. An odd number of negatives means it's going to be negative. So we have negative x to the 4th. Here there is a negative and then 3 more negatives. That's an even number, so it'll be positive 3x to the 3rd. Here there is 1 positive and 2 negatives. That's an even number, so it'll be positive 6x squared. Here there are 2 negatives. It'll be positive 4x. And finally, negative 12 will stay negative. So counting our sign changes of f of negative x, we have 1. There isn't a sign change here. There's not one here, but there is one here. So we have 2 total, which means the negative real zeros are either a total of 2 or 0. And again, I apologize, this got a bit cramped here. The next problem won't be nearly as cramped. But so there are either 2 positive real zeros or 0 positive real zeros, meaning there cannot be 1. There cannot be 3. There has to be exactly 2 or 0. So if you find a positive real zero, there has to be a second one. And the same thing for the negative real zeros. If you find 1, there has to be another 1. So that helps you when you're checking these possibilities. So determine the possible number of positive and negative real zeros of f of x equals negative 5x cubed plus 2x squared plus x plus 5. Take a moment, pause the video, see if you can solve this. Okay, so going through this together, counting our sign changes, we have 1 and then no more. So, as for the positive real zeros, there is only 1. There cannot be -1. When you subtract 2 from this, you'd get -1, meaning there is exactly 1 positive real zero. We cannot say there's 0 because that's not an even multiple less than 1. Now we find f of negative x. So we have -5 times negative x cubed plus 2 times negative x squared plus negative x plus 5. when we substitute in negative x into this function. Here there are 4 negatives, so it's going to become a positive 5x cubed. Here there are 2 negatives, it's going to become a positive 2x squared. Here there's 1 negative, it'll be minus x, and then plus 5. So f of negative x is 5x cubed plus 2x squared minus x plus 5. How many sign changes do we have? We have 1, 2. So the number of negative real zeros is 2, or an even number less than that, which is 0. Just a quick note, if we had found 4, for instance, then there would be 4, 2, or 0 possible negative real zeros. Any even number less than that.